Before we start talking about systems that have more than two variables, that's basically what we're getting into. I wanted to talk about the graphs of an equation that is something like this, just for example, like x plus y plus z equals, I don't know, 3 or something. This is instead of just like x plus y equals 3, where we would have produced a line on 2D space. Let's talk about what the graph of something like this would look like. And let's even go even further back before we talk about that. Let's talk about something like x equals 3 and how we would have graphed that. X equals 3 would have been something like this. We'd start with a number line in, I don't know, first grade or something. And there's 0 in the middle, and then we come over here 1, 2, 3. And we would have said, well, x is 3. It just is 3. That was the only option. Okay. And then we moved on to something like x plus y is 3. Okay. So what we did at this point was say, well, this number line can let me graph one thing, one variable. But I need a way to graph two variables. So what we did was add another axis. And we said, we'll graph the x one here. And then once we're at the x, whatever y we need, we'll graph it up here. And this is the positive y and the negative y. So for x plus y equals 3, this still works. X is 3 and y is 0, and if we add those together, it's 3. Well, if x is 2, then y would have to be 1, so we'd graph that there. Right? And if x was 1, then y would have to be 2, because 1 plus 2 would be 3. And then if x is 0, then y is 3. And if x were negative 1, then y would be 4, and so on. And then there are all these other solutions in between the ones that we marked, like, say, if x was a half, then y would have to be 3.5, and so on. So there's all these solutions. So we connected all of them. And all these were solutions to this equation. But now think about this. Originally we had one dimension. We would graph something on the x-axis and just tell what x was. Then we said if x is this, then y is this. We graphed two variables, the x and the y. Now if we have something like x plus y plus z equals 3, we need more room. We need some other place to account for this z variable, just like we drew the y-axis to account for the y variable. So how can we do that, especially when we draw on a piece of paper that is two dimensions? Well, we're getting at the problem here. We only have two dimensions, and apparently what would help is if we had a third kind of dimension. And there's actually not just one way to do this, but the way that we conventionally do this is at the same reasoning we used to go from the x-axis to the y-axis. We're going to add a z-axis. This went left to right. This went up and down. This axis is going to go front to back. Right? It's going to go right through the middle. It's going to have a positive and a negative as well. Okay. And conventionally, the z-axis is what we call this axis. This is the x and the y, and we have the z here. Whether it makes sense or not to you, whether it's intuitive, to me it's intuitive that x is positive to the right and y is positive up. Z is positive toward you. This side, let's make this side bigger. And then it tapers off and gets smaller if we understand perspective in drawing. Since this side is bigger, it's coming towards us, it's closer to us. And this is positive. This would be the positive direction, and way back here would be the negative direction. Okay. So as much as we can grasp it, we can graph this thing. X plus y plus z is 3, right? So if, remember I said at the beginning for the two dimensions, if x were 3, then y would have to be 0. Let's do that again for the 3 dimensions. If x were 3, y and z would both have to be 0. There'd be no choice about it, because x is already, well, actually, if x were 3, then y could be positive 1 and z could be negative 1. Okay, so let's show that. If x were 3, then y could be positive 1, and z could be, and we're going to go in the negative direction, could be negative 1. Okay. If x were 3, y could be negative 1, and z could be positive 1. So y could be negative 1, and z could be positive 1. Okay, let's try, and you could keep going with that. X could be positive 2, and z could be negative 2, and so on and so forth. If x were 2, then let's do something that kind of makes sense. If x were 2, then y could be 1, and z would be 0. Right, so here we go. If x were 2, then y could be 0, and x could be 1. So we got 2, 0, and positive 1. Okay, you see where I've got this going here. If x were 1, then y could be 1, and z could be 1. So x could be 1, y could be 1, z could be 1. I'd put it right around in here. And we could graph all of the possibilities, just like we could graph all the possibilities in 2 dimensions. And the question that I want to pose is, if we keep graphing these things, keep graphing all these possibilities of all the things that x and y and z could be, and add up to 3, what kind of shape would we get? In 2 dimensions, we would have graphed them all. If we linked them all together, we got a line. So what kind of a shape would we get in 3 dimensions? Now, my first instinct when I first learned about this was that it would also be a line. It would just shoot off in 3 dimensions. You know, it doesn't just stick on the piece of paper. It could come shooting out this direction or something like that. Maybe that was what it was. You know, a line in 3 dimensions. So it could be a line that comes out towards you and moves away from you at odd angles and so. But then I started thinking, I know in 2 dimensions, the solution to a system would be like 2 graphs. So a simple system would be 2 lines, and their intersection was the solution. Wherever those lines cross is the solution. And I can, in 2 dimensions, a lot of times, unless the 2 lines are parallel, they're going to eventually run into each other. But in 3 dimensions, if there are lines in 3 dimensions, and the solution is where these graphs intersect, what are the odds that 3 lines shooting off in 3-dimensional space are going to run into each other? It didn't seem like there was a very good chance of it, and yet, I was doing this work with systems of 3 equations and finding solutions all the time. So, how could it be that if the graphs were these lines, just lines shooting off in 3 dimensions, wherever we wanted, just laser beams shooting off willy-nilly, how is it that they would run into each other? The answer is, let's go back to the 1 dimension. The 1 dimension, we started at x equals 3, and we put a dot there. That was 1 dimension, was a point. It's this little dot. And then in 2 dimensions, it was kind of like a 2-dimensional dot where we expanded our minds. You could imagine looking at a line from the end. If you looked at a line from the very end, it would just look like a dot. But then if you peeked around to the side, you would start to see that there's this line behind it. It's kind of like looking at a broomstick from the very top. It just looks like a circle. But that is, as you peer to the side of the broomstick, you see, oh, there's this stick behind it. And in the same way, what we've been doing is kind of looking at this 3-dimensional figure from the side. What would this 3-dimensional figure be if I stopped looking at it from the side and I kind of peeked around the corner to see what was really there the whole time, well, it's kind of look like looking at the side of a piece of paper. If you just look at the side of a piece of paper, you just see this line, but as you start to peek around, you see, oh, there's this flat surface behind there. And we call that a plane. So if you imagine pieces of paper, not just laser beams shooting out all over the place, but pieces of paper shooting out in random directions, it's pretty simple to imagine they're intersecting. Like eventually those pieces of paper are going to hit each other. Definitely two pieces of paper have a high probability of hitting each other, right? If I had this piece of paper shooting off like this, and another piece of paper, say, going off this direction, then you could imagine, of course, these represent planes that go off for infinity in every direction, and so somewhere pretty soon they're going to be intersecting these two pieces of paper somewhere in this area. Now imagine I put a third piece of paper, because that's the kind of systems we're dealing with, is three equations and three unknowns. These guys are going to meet up over here. They're going to meet up, you could probably imagine, a line, something like this. And then this third piece of paper is going to shoot in there, and it's going to intersect with those two, maybe like right here. And you can imagine that if you were to take three pieces of paper and throw them out there at random, and they just land where they may, most often those randomly thrown pieces of paper are going to intersect in this kind of a way, where this one's kind of this direction, this one's oriented this way, and this one this way. And imagine how those three would intersect. They would probably intersect. These guys right here would probably intersect. These guys would probably go like this. They're going to meet right there. And this guy right here is going to meet them kind of along here. And this thing right here, this point right here, is the only place where all three of them are touching each other. Like these guys are touching here, and this guy is touching both of these along this path. Actually, it would probably be touching them more like this one would intersect along this line here. This one would intersect along this line here. Let me erase these other two. Right, and you can see like this. It's almost like the corner of a room, where this would be like the floor, and these would be the walls of this crooked, sideways room. And that corner of the room is where they would all intersect, and most often that's how they'll intersect, is at a point, if you imagine them thrown together at random. So keeping that in mind, let's think about all the different ways that three planes, three pieces of paper, could intersect. Their intersection could be like we just talked about, where here's one plane, and here's a second plane, and here's a third plane. These are shooting off at each other like this. This one's flat like that. Of course, they could intersect in lots of different ways, but generally in a way that looks like the corner of a room, sort of. It could be like a really narrow room, or you could, they might make a shape like this if they were all really, angled differently. If you could imagine these three pieces of paper going like this. This one is back here, and then this would be the point where they're all intersecting. I'm just showing you sections of the plane. Here's one, and here's another one, and here's a third one, and they're all pretty steep, but they all meet right here at that point, and that's going to happen most of the time. They're just going. If you were to choose three pieces of paper at random, they would meet at a point. So let's think about all of the ways that they could intersect, that three pieces of paper could intersect, and therefore how many different kinds of numbers of solutions that three equations with three variables can have a solution. how many solutions that those systems can have. So 1 at a point, that's where they all intersect, is at one point. Or say I had a piece of paper like this, a plane like this, and another one like this, and they meet together kind of like a book, like right at the spine. And, planes are going to do that. You take two planes and they're going to intersect and they're going to make a line. That's going to happen. What if that third plane just happened to be running right alongside that line? I'll just extend where we can see this plane out to there. Okay, it's like this big one that is big is like a desk, and these are like coming together like a book sitting open on a desk. Okay, but a very thin book of one page and another page. It's almost like a folded piece of paper, and that folded piece of paper could represent two planes. They intersect together at a line. They're sitting on this desk, and the intersection is still this same line. And if these keep going on forever, that intersection would go on forever. So how many solutions would there be? Well, they intersect here and here and here, 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 and on forever. They would keep intersecting. So, of course, this would be an infinite number of solutions. All right. What about say I drew this plane like this, it's shooting off into the sunset, and say I had another plane and it is exactly in the same place. Remember, this is, the same as if two lines were right on top of each other. They were the same line. So now I have two planes, they're in exactly the same place, and I draw the third plane and it's exactly in the same place. They're just right, even more severe than right on top of each other. They are the same plane. They intersect here. This point right here is a solution for this plane that's on quote-unquote on top, and it's the same for the one that's in the quote middle and the bottom. There's another solution there. Any solution on any one of the planes is a solution on the other two planes. So this is another kind of infinite number of solutions. How about if I had one plane going like that. Let's say another plane that's also standing kind of straight up goes off like something like this, and it's it's back here, it's behind this, and this other plane is cutting through these two planes. I know this is weird to think about, but these two intersect back here. Okay, these two intersect here. These two intersect here. But for all three of them, to have a solution together, they would all have to intersect together in the same place. But if you imagine all these three planes like standing straight up, then in a way they're kind of parallel, and so they'll never intersect each other, all three at the same time. These two will, and these two, but not all three at the same time. So this would be no solutions, 0 solutions. Okay, what about, say if I have a plane here, directly underneath that I have another plane, directly under that I have another plane, and say they're all perfectly flat. If they're all perfectly flat and one is above the other and above the other, then they'll never intersect either. If they shoot off for infinity in all directions, they're still not going to intersect. So that's another kind of 0 solutions. Okay? And the only thing we're trying to gain here is the idea that we can have one solution, infinite solutions, or 0 solutions. Okay? And that's the only kind of intuition that we're really trying to gain. And we're not having to graph these things. You're not going to have to worry about that. But I think, and I'm sure I'm right, that if you spend the time to listen to this explanation and you have this intuition about why there are the number of solutions there are, and what these graphs look like in 3 dimensions. Envisioning these things and understanding the solutions to 3 equations and 3 unknowns will be a lot easier for you. Okay, so now let's get into the actual problems, the kinds of problems that we're going to see. Let's talk about what a definition to a system would look like. Well, a system could be something like this. X plus y plus z, we have this third variable z equals 2, and x plus y minus z equals 7, and x plus, actually let's make it, it's a fairly simplistic system. These could all, this could be 2x and 5z, it doesn't matter. Minus y plus z equals 13. So what would a solution to this system look like? Well, it's going to be this ordered triplet, an x and a y and a z. This x can go here, here, and here. This y goes here, here, here. The z goes here, here, here. And when I put that same x, y, and z into all these equations, here I'm going to get a 2, here I should get a 7, and here I should get a 13. Okay, now the solution, I chose these numbers at random. I would be willing to bet that it does have a solution, and that it's most likely just one solution. The solution might not be so nice, is what I'm trying to get at. It might be fractions or whatever, but I'd be willing to bet there's a solution out there. And I'm not worried about finding it. I'm worried about just understanding what a solution would look like, and it shouldn't be too difficult to understand that this is what a solution would be, since we have our experience with 2 variable systems. So the first thing we want to be able to do is just to verify that something is a solution to a system. Okay, so wanting to practice that, let's use this guy here. Make sure to skip these boring parts. I'm just writing stuff down right now. I hope you're not listening to this or watching this. Okay, so what this example proposes is that 1 comma negative 1 comma 2 is a solution. Whether it's the only solution or not is not the question here. Finding that solution is not the question here. Just testing the solution is the question. So here, when you start working with these guys, it can get pretty confusing. So let's do 3 different colors like that. So the first one, I'm going to write in blue here. The 1's going to go in for x, minus 2 times a negative 1 for y, plus 3 times 2 for z, and there we go. So let's just try this out. Negative 2 times negative 1, that's going to make us add 2, plus 3 times 2, that's going to be 6. That's 6 plus 3, and that is 9. So it works here. Let's try the second one. Negative 1 plus 3 times negative 1 plus 2 for z equals negative 2, we hope. This is negative 1 minus 3 plus 2. So negative 1 minus 3, that'd be negative 4, plus 2 is negative 2. So it checks out here. Red. 2 times 1 minus 5 times negative 1 goes in for y, plus 5 times 2 goes in for z. We hope that equals 17. This is 2 plus 5, negative 5 times negative 1, plus 10. This is 7 plus 10, that is 17, and that one checks out. So yeah, this is a solution. Okay? That's all we're looking at. We're just trying to verify that something is a solution, which means we're going to plug it in. Alright. Now let's start to look at starting pretty simple, coming in nice and easy. Um, we're going to find the solution of this system. And I think that once I get it all written down, it'll be pretty apparent how we're going to find the solution to this system. Z and Z equals 2. Okay. So, we're trying to find three numbers, x, y, and z, that you can plug into this and this and this so that they all become true. Right? So the same z would have to be used here and here and here, and likewise for y and x. But if the same z is supposed to be used for here, here, and here, the z that works here is 2. Z is already given to you. Z is 2. So, all I would have to do to find y is take this and put it into this equation, and y would become quite apparent. So let's do that. Let's plug z into this equation. Y plus 4 times 2 equals 7. Y plus 8 equals 7. And y equals negative 1. Fantastic. So y is negative 1. We've got z is 2, and y is negative 1. And so now we take the fact that z is 2 and y is negative 1, and if 2 works for z here, and negative 1 works for y here, then negative 1 should work here for y, and 2 should work for z here. So let's try that one out. X minus 2 times, we're going to put negative 1 in here for y, plus 3 times 2 for z equals 9, we hope. And x plus 2 plus 6 equals 9. So x plus 8 equals 9, and x equals 1. So there's that. So the solution is x is 1 and y is negative 1 and z is 2. That might look familiar to you. That's the solution to this system. And actually, this system here and this system down here, they're actually the exact same system. We changed that original system into this system using what we call elementary row operations, and I'll talk about that in just a second. But just a couple things here, a couple of vocab things. We took z and we went back to this equation and we substituted it for z. And we took z and y, once we found y, went back to this one, we substituted for y and z and found x. So that method of substituting, into here and then, or first into here and then into here, is called back substitution. Okay? Now, take a look at the shape of this system. If you see a system of 3 equations, and you can draw this set of stairs here, where you come over, you have one less variable here, one less variable here. That's called row, should be a hyphen, echelon form. Okay, so remember I said that the system that was up there, out of the screen right now, and this system were the same system, and so we would say that we took that first system and we put it into row echelon form, and we used elementary row operations. So let's talk about elementary row operations. That's how we can take a system, put it into row echelon, and use back substitution to simply solve the system. So there's 3 kinds of elementary row operations. Okay, let's make sure that I keep it in the same order as the book. Okay, the first thing that we could do is we can interchange 2 equations. 2 equations, or 2 rows, because the equations come in rows, 3 rows. And whether this equation is first and this is second, or if they've switched roles and this one's first and this one's second, this one's third, it doesn't matter. The same x, y, and z need to go into all three of them, and it doesn't matter which order I write them in, so I can switch the order, and sometimes that's helpful. So that's the first thing we can do, is interchange two equations. The next thing that I can do is multiply, forgive my abbreviations, multiply a row by a scalar. And a scalar, something that scales, we can scale it up or scale it down, make it bigger, make it smaller. That's just a number. A scalar is a number. I could take this equation here, whatever it was, and multiply it by 8, or I can multiply it by -3, whatever I choose. It doesn't change the x, y, and the z that would have to go in there to make it true. If I make this x 8 times bigger, and this y 8 times bigger, and this one 8 times bigger, and the answer 8 times bigger, the same x, y, and z still need to go in to make this true, as when it wasn't multiplied by 8. And yeah, our skills should be such that we would be convinced of that. We wouldn't have a problem with it. Okay, so we can interchange rows. We can multiply a row by a scalar, which is just a number. And the third thing that we can do is essentially just add to. Okay, and understand, when I write equations and I write row, they are interchangeable. They're the same thing. So add two equations slash rows. Okay, just so that we understand they're the same thing. Together. Okay, I can add them as they look when they give them to me. I can multiply this one and add it to this one. Whatever suits me, I can do that. Okay, so let's give it some practice. Let's take this system. Remember, fast forward through this. I have to sit through this, but you don't. You have a little fast forward slider here. Don't blame me if you're sitting there for too long, getting bored by what I'm saying right now. Okay. So whatever I want to do in the confines of those three rules, those three row operations that I can do them. So what we're going to do here is use elementary row operations, try to get this thing into row echelon form. Get a little practice in that. And given our experience in two variable systems, we are familiar with elimination. Right? To get from here to row echelon form, where I have that step shape, I would need to get rid of this x here, and this y here. And I kind of am oversimplifying it, because I might want to get rid of this x and this x and this y and interchange these two rows or whatever. But let's just see what we can do. Let's use our thinking skills and imagine how we could get it into that row echelon shape. So the first thing that I see when I look at this is, and that I'm thinking, I got to get rid somehow of two x's. I got to leave an x, y, z up here, have just a y and a z, and have a z just here. So the first thing I'm going to do is get rid of an x here and an x here. However, I can do that. Well, here immediately this is simple. I can take these two guys and I can add them together, and the x's would eliminate each other. Okay. Now, when you make that addition, you're going to replace one of those equations that you used with the new equation. Let me show you what I'm saying. I'm going to take, I said I'm going to add these two together because I'm seeing that these x's are going to cancel out. So let's do that. X's cancel out. 3y minus 2y is going to leave 1y. And 3z plus z is going to be 4z. And 9 minus 2 is, on the other side, is going to be 7. Alright, now I have this new equation that I've created, and since it's missing this x, which is what I want, I'm going to, instead of writing this, only because it's one of the equations that I used to add together, I'm going to replace that with this new thing. Alright, so I have a new system. So this guy is going to come and replace the second one. This one's going to kind of go away in a manner of speaking. It really just got changed into this guy. So this is going to be y plus 4z equals 7. And then this is just the same as it was. Y plus 5z equals 17. Alright. Now I'm looking to get rid of this 2x. Okay, this is what you should be doing every time, is get rid of the x in the second equation, the third equation, whether you're switching equations around, whatever. I'm going to get rid of this next x, cancel it out. Well, I want to use this x clearly to cancel it out. I would need a negative 2x here to cancel with this, so I'm going to multiply this by a negative 2. So I'm going to change this by multiplying by 2. Hopefully that, let's see, maybe if I put parentheses it will be a little more helpful. However you want to imagine it. You could put a 2 over here. Whatever helps you to keep track of this. It's kind of hard to keep track of, kind of messy. So I'm going to multiply this by, actually, negative 2, right? I want a negative. So negative 2x plus 4y minus 6z equals negative 18. Okay. Now I have an equation that if I were to add this to it, I would cancel out the x's. So let's do that. Let's move this over here just to help keep track of everything. And we're going to add these together. You don't have to be this detailed. I just don't want to confuse anyone. So I'm making sure to write down as many steps as I can think to write down. Okay, so I'm going to take this new equation. I'm going to add it to this third equation. We're going to have 0x negative y. 5z minus 6z is going to be negative z, and this is going to be negative 1. Okay, so we've got this new system. We're going to take this guy and it's going to replace our third equation because it's no longer got that x. Plus 4z equals 7. And this one's going to be our new third equation, negative y minus z equals negative 1. Alright, we're almost in row echelon form now. The only thing we need to do is get rid of this y. Well, now be careful. This, until you get the hang of it, it can happen a lot. You might try and use this equation to cancel out this y for some reason. But if you do that, then when you add them together, this x is going to come back into the equation. So make sure that you do this in a nice order where you get rid of the x's, which we've done, and then you're going to get rid of this y with this equation, because now this is basically a system of two equations, right? And if I had the system of two equations, I would cancel out these y's. I wouldn't come in with this equation that has three variables and try to work with it, this and that. Okay. So it's already set up really nicely. It's already, they want to cancel each other already, so I'm just going to add these together, and I will get y minus y is no y's, 4z minus z is 3z, and 7 minus 1 is 6. So now I've got this new system. I'm going to move over here since I'm running out of vertical room. I'll go horizontal. My new system, let me just put a squiggly here, separate. So my first equation comes over, it stays the same. My second equation comes over, y plus 4z equals 7. And now my new third equation, 3z equals 6. Alright. Well, now you can see it's going to be pretty straightforward. Z clearly is going to be 2. Z is 2. I'm going to put 2 into this equation. I'm going to do that over here. Y plus 4 times 2 for z equals 7. So y plus 8 equals 7. So y is going to be negative 1. And we're going to put negative 1 and 2 in there for z. I'm going to do that here, right? It's this equation. X minus 2 times negative 1 plus 3 times 2 equals 9. We've got a 2, a positive 2, plus 6 equals 9. That's 7 plus x equals 9, so x must be 2. Right? Let's see. 6. Oh, sorry. 6. It's 6 plus 2. 6, 7, 8, of course. 8 plus x is equal to 9, so x must be 1. So our solution, we've got x, y, and z. 1, negative 1, 2 is our solution. We used elementary row operations to get us down to row echelon form, used back substitution, and there we go. And that's really the basic idea behind this whole thing is using the row operations to cancel out things and get it into row echelon form. That's our basic skill. In the practice problems, we'll look at things where we have infinite solutions, no solutions, and so forth. So I look forward to seeing you there.